Hello, everyone. My name is Janet Kelsey of Separation Science, and I'd like to welcome you all to our latest webinar in collaboration with Biotage. Our topic today is automated sample prep, transforming the future of PFAS analysis. Let me introduce our presenter for today's webinar. Evan Walters is a regional market segment and applications manager for Biotage and has been with the company for 7 years. He is passionate about science and analytical chemistry in the environmental, food, and agriculture market segments. He has previously held roles as an environmental chemist, geochemist, and technical sales representative. Walters received a Master of Science in Geochemistry from Southern Illinois University. So, without further ado, I'll hand over to Evan.
Yes, thank you for the introduction, Janet. And yes, today we will be discussing automating sample prep for PFAS analysis and really comparing some of the previous EPA methods along with the newer EPA methods such as 1633 alongside the newest DIN EN method 17892, all looking into what automated platforms we can utilize for the sample prep. So outline for today's presentation is we are going to go over the workflow for PFAS testing, just a overview of, sample in, data out. Then we'll be looking at the analytical methods mentioned in this presentation. From there, we'll take a look at the newest addition to the Biotage automated solid phase extraction platform, which is the Prep Expert 8, as well as some performance criteria for PFAS and beyond. And then finally, we'll summarize the presentation and open it up for questions. So here's an overview of the PFAS sample preparation workflow. And whether you're processing solid samples or liquid samples, your process all traditionally goes through the same workflow and eventually ends up at solid phase extraction. And this will be the highlight of today's presentation as we dive into some of the automated platforms offered by Biotage. So if we look at the automated SPE platforms for sample processing, we have the Biotage Extrahera to the left. We have the newest edition, which is the Biotage Prep Expert 8. And then to the right, we have the Horizon 5000. All of these automated systems have their own unique features that allow them to be utilized for different sample matrices and volumes. But typically, just broad stroke, Extrahera system is going to be used for your smaller sample volumes or your cleanups of your sample extracts from solid processing, and really ranges from 50 microliter volumes to 50 milliliter volumes at max. The ideal matrices for this system are soils, biosolids, tissues, biofluids, food and ag products. And we already have several laboratories using this system for PFAS sample prep of these matrices. Now, the Prep Expert really fills in the gaps between the Horizon and the Extrahera system. And the nice thing about the Prep Expert is it can handle a wide range of matrices between drinking water, groundwater, surface waters, and even some wastewater samples. The volume range for the Prep Expert 8 is anywhere from 10 to 1,500 mils, but you can also process larger volumes if you wish to. Now, the Horizon 5000, this system also processes larger sample volumes, and this system is really ideal for your extremely challenging wastewater matrices. So if your samples have oils in them, grease, high content of dissolved solids, and total suspended solids, this might be the best option for you. But for now, we're going to focus on our newest addition to our portfolio, which is the Biotage Prep Expert 8. So since the Biotage Prep Expert 8 is ideal for aqueous samples, let's take a look at the different EPA methods alongside the DIN method and see what matrices are referenced in these methods. As you can see for EPA 537.1 and 533, these methods are referencing drinking water samples, whereas the EPA 1633A method references ground, surface, wastewater, and other solid matrices. DIN, for example, allows all matrices to be applied to this method since it is a performance-based method. And as you can see, both the EPA 1633 and the DIN method are performance-based methods, meaning you do have some flexibility in what matrices can be validated for your lab, as well as the sample volumes. Now, when we move to sample volumes, you can see EPA 537.1 and 533, these are prescriptive methods. So there's not much flexibility in the volumes and samples that they apply to. Most of the volumes that are covered in these methods are greater than or equal to 100 mils. And the reason why that is it improves the method detection levels. So the more sample that you are extracting, the lower you can see in terms of detecting PFAS compounds. So now that we kind of understand what matrices are applicable to the Prep Expert 8, let's take a deep dive into the system and look at some of the performance criteria. This is our consolidated workflow for liquid samples. You have your pre-treatment, your solid phase extraction, your concentration, and your analysis. And for PFAS analytes, typically most labs are running it by LC-MS-MS. So when we navigate the testing methods or the analytical methods for PFAS analysis, we don't have to look too far back in history to see how much development has been done in the last several decades. In 2009, the EPA came out with its first official drinking water method, and this method targeted 14 PFAS analytes. From there, as part of the UCMR3 program, the EPA expanded their method to 537.1, which had 18 compounds, including Gen X. And then shortly afterwards, EPA method 533 came out with 25 PFAS analytes, and it was developed using a wax SPE versus the traditional DVB that was used in 537. And this was done to improve extraction of short-chain PFAS analytes. And finally, last year in 2024, EPA method 1633A was finalized by the EPA and the Department of Defense for detection of 40 PFAS compounds. And in the same year, the DIN EN method 17892 was created for 29 PFAS analytes. So a lot has been done for testing PFAS, and improvements in these analytical methods, as you will see, have been made along the way. So each method has target analytes, and as we went from 537.1 to EPA 1633 and the DIN method, we have also expanded the number of target analytes. And so I created this slide to kind of take a look at what analytes are in the method. And when you consider 537.1 and 533, there are 29 unique PFAS targets that are in these methods. All 29 are also referenced in EPA 1633, which has 40 targets. Now for the DIN 17892, this method has 29 targets. But what we did to expand upon the DIN method is we also included targets from the ISO 21675 method. So our method actually looks at what we call the extended DIN list. And so overall, what we are going to look at are 48 total PFAS compounds. And between the 1633 method and our expanded DIN method, there are 48 total unique compounds. However, most of them are shared between the 1633 method and the DIN method. But there are a few unique ones to each method, And as you can see from this chart, the DIN method has some longer chain PFAS, which will give us some different considerations, also some shorter chain PFAS. But the best way to look at these target analytes is to plot them by carbon number. So here's a plot that kind of gives you an insight to their chemistry. And on the x-axis, we have the number of carbons in the chain of the PFAS analyte. And then on the y-axis, we have the number of these analytes that are found in the method. So for instance, in the extended DIN method, there is one analyte that has 20 carbons in its chain. And that's important to understand because that analyte will have it will not be as soluble in water. So it'll have hydrophobic interactions because it has so many carbons in its chain, meaning it will crash out of solution if there's too much water in the extract, or it will stick to surfaces such as the plastic container of the sample bottle or some tubing in your system. So there is a lot of considerations when you're analyzing very, very hydrophobic PFAS targets, or even on the other end of the spectrum, very hydrophilic. But you can see the extended DIN method compared to the EPA 1633 method has expanded the range of the chemistry of these analytes. So now that we understand a little bit about the method history and the method that we will be looking at for this presentation, let's look at the performance of the newest addition to the Biotage family, the Biotage Prep Expert 8. We'll take a look at three different categories, the PFAS system acceptance criteria. We'll also look at PFAS operational improvements using the Prep Expert 8, and then some features beyond PFAS testing. Starting off with PFAS system acceptance criteria, let's take a look at identifying the low background in the system. When you're testing for PFAS, these compounds are very ubiquitous in the environment, so making sure your system has low PFAS background is highly important. And really, there's three things to consider when identifying if your system has low background, and they're all related to your analytical calibration. First, you need to understand what your concentration range is for your method. So if you're screening for PFAS compounds, you need to understand what range you're screening for. And then you need to determine your lowest calibration in your cal curve. So on your analytical system, you need to know how low you need to calibrate, which then also allows you to identify if your system does have that low background for PFAS compounds. And it all gets a little bit tricky. Methods have different nomenclature for different terms in terms of, method detection limit, reporting levels, calibration points. So, I had to normalize these terms, and what I did is I created this diagram, which I think is very helpful. On the left-hand side, we have no detect, and then we have a line that increases in concentration. And so your first point right here, this is your system calibration point, number 1 in nanograms per liter. So this is sample concentration. And then typically from there, you'll have your your method detection limit. So this is what you were able to identify as the lowest detection limit that is reproducible on and that includes your analysis and your sample extraction. From there, we have what we call the minimum reporting level, or 1/3 the minimum reporting level. So most labs do not report at their detection limit. They report at a concentration that is higher than their detection limit. So when you find your minimum reporting level, then 1/3 of that minimum reporting level, that is where your blanks should be below. So a laboratory reagent blank should be at least less than 1/3 the MRL. And that is how you'll be able to identify whether or not your system has low background. And just for some other terminology, Usually your minimum reporting level is also the lowest level that you spike at when you're doing ongoing precision and accuracy. So when you want to make sure that your lab is keeping up with its quality requirements, you will spike at a low level and just make sure that you're still getting good precision and accuracy. And then from there, at higher concentrations, we have our ML or our mid-level ongoing precision and accuracy. And then we have our high-level ongoing precision and accuracy. And this is kind of overall arching view of detection levels and how to really determine whether your system has low background. So now that we kind of have an understanding of what these terms mean and what we're actually looking for when it comes to background levels, let's figure out what our lowest calibration should be. And when you look at different EPA methods, you can see, if we go back to here, we have 537.1. This method is plotted here. These are the method detection levels. And we know we want our background lower than these method detection levels, or at least at these method detection levels. But they're not very low. And that's because the method's older. The analytical capabilities weren't as well defined as they are now. So let's see if we can get it even lower than that. And when we look at EPA 533, strange thing is this method actually doesn't have method detection limits associated with it. It has what it's called the lowest concentration MRL. So that's your low level spike. So there isn't really a defined method detection limit. Now for EPA 1633 aqueous samples, there is a defined method detection limit, and you can see it's in this blue line right here. So it floats between 1 nanogram per liter, plus or minus. And then at the end, you can see there are some very, very high method detection levels. And it's strange because these really aren't that hard to accomplish. And the reason why these are so high is because when the method was first being developed, the standards that were available were at higher concentrations uh, than the other analytes. So if you can see where the Cal 1 was for the EPA 1633 method, the MDLs are very closely aligned to where the first calibration point is. So you can see when there's spikes, usually there is a spike in the calibration. So it's important to define what your Cal 1 concentration is, because that will actually help you reach lower detection limits and also help you identify if your system has acceptable background. So for us, we decided, 1 nanogram per liter. That was a point in which, anything lower, we really wanted to get to see what was there. So let's zoom in at 1 nanogram per liter. So when you zoom in at 1 nanogram per liter, you can see what we have done is we set that 1 nanogram per liter as our MRL. And so this is our lowest spike level. And what that creates is a 1/3 MRL, which is 1/3 this 1 nanogram per liter adjusted for salts when your compounds are in their salt form. And you can see our goal was to have our compounds below 1/3 the MRL on the Prep Expert 8. And I also have the EPA 1633 Cal 1 in nanograms per liter. And you can see, again, the different concentrations for different PFAS. Here, these are not compounds that are actually listed in 1633, so you can see it stops right here. And then I have right here in the blue dotted line our Biotage Cal 1 in sample concentration. And you can see after 8 replicates of laboratory reagent blanks, here is the result in terms of background. So all background on the Prep Expert 8 was below 0.1 nanogram per liter. And this is above and beyond what method criteria were for all methods that we considered. So now that we know that our system has acceptable background, let's look at the precision and accuracy by method. And you can see For the EPA method 537.1 and 533, the accuracy or percent recovery is acceptable between the range of 70 to 130%. And that is for all analytes referenced in those methods. For 1633A, it varies by analyte, and you can see how it varies looking at table 5. And then in the DIN 17892 method, it actually doesn't have accuracy demonstration requirements, but it has matrix performance data. So it goes over a few different matrices and how they performed. And those can be found in table A.5 to A.7. Now for precision or percent RSD, again, EPA 537 and 533 is less than 20%. EPA 1633, again, varies by analyte. And then the DIN method also has the matrix performance data, but doesn't have precision requirements that are specific to the method. So when we look at this for EPA 1633 and see how the Prep Expert 8 performs, this is the list of the 1633 natives. And this is 8 replicate spikes. And again, remember that these concentrations vary by analyte, so the range is anywhere from 22.2 to 625 nanograms per liter. So a pretty vast range, which is just due to the fact that these concentrations of these analytes in these standard solutions are varied. But you can see the recoveries on the Prep Expert 8 all fall within the acceptance criteria for the EPA method, and you can see that's in the red dotted line. And then for the 537 and 533, I just added these for the 70 and 130%. So you can see that not only does the Prep Expert meet the 1633A requirements, but also even more strict requirements of the 537.1 and the 533. Here's the precision for the 1633A natives. Again, I have the 1633 RSD limit in red. So this varies by analyte, and you can see how it varies, anywhere from 20% RSD to just below 40%. So there is high variation in this method in terms of RSD, and it can still meet the acceptable requirements. Again, these are the same 8 replicate spikes at the range of 22.2 to 625. And I also added in the requirements for 537 and 533 at 20%. And you can see all the analytes except for one analyte, which is net fossa A, all of them meet the 1633A requirements as well as the 533 and 537. But what about net fossa? That one's above the 537 requirements. It's not found in 533. It's only a 537.1 and a 1633A required compound. So I added a question: is this due to the elution solvent volume? Well, let's take a look at analyte carryover. Analyte carryover is very helpful information because it tells us if compounds A will carry over to your next sample when you analyze it. And it also tells us if we're using enough solvent to extract the sample or the analytes from the system. And so here's a study that we did where we spiked 8 LFBs at very high concentrations, 400 nanograms per liter, and we extracted them. And then what we did is we cleaned 4 positions, and then we extracted 4 blanks right after we cleaned the 4 positions. And then we didn't clean 4 positions, and then we extracted 4 blanks. And you can see the orange bar is the blank recovery after it was cleaned. And you can see all of those blanks are below the 0.5 nanograms per liter. And when we didn't clean it, you can see we had some hits that were over 1/3 the MRL. And sure enough, it was net fossa A, and even net methylphosa A. So it is important for some of these compounds that are a little bit stickier to make sure that you're using enough solvent in your SPE elution scheme and you're using enough solvent to clean the system internally before running your next sample, or you can get a false positive. And when we compare the SPE elution volume, you can see that 537.1 uses 4 mils twice of methanol, so 8 mils total elution solvent, whereas EPA 1633A only uses 5 mils of elution solvent. So it may be the variation in the net fossa is actually due to the fact that EPA method 1633A doesn't use as much solvent for elution when compared to 537.1. Now let's take a look at the extended natives, the DIN natives recovery. And you can see, again, most of these analytes are well within the EPA 1633A low limit and high limit where they are shared. And you can see this where it does not have the red dotted line. These are your compounds that are not within the EPA method for 1633 or 533 or 537. And most of them fall within the 130 to 70% recovery range, except for fossa A. And this compound we find, although it's not actually listed in the DIN method, it's part of our expanded list. That's actually part of the ISO method. It's a very challenging compound, and it also required us to improve the SPE chemistry and technique. So we'll talk a little bit more about that later. Now, when we look at the extended DIN natives precision, again, this is at 1 nanogram per liter, so a pretty low level spike compared to the 1633. You can see that the 1633A compounds that are found in this extended method, the RSDs fall well below that. Now, the 20% RSD that we added for a little bit more of a challenge, again, the fossa A, which we kind of just talked about, it was outside of that 20% RSD. And then the PFOCDA, or the octadecanoic acid, this also fell. Although it met the recovery requirements, the precision wasn't as good as the other compounds in the method. And this is another challenging compound. This is a C18 carbon chain, so it's very hydrophobic. So it could be a product of needing more solvent for an effective elution and making it more consistent. Both of these are not part of the DIN method. They're part of our expanded DIN method. So just keep that in mind. All right, so we've been through precision and accuracy on the Prep Expert 8 system. We've found that, for the most part, it's met all the requirements for 1633. There was some interesting case with the net fossa, which fell above the requirement for 537, but we believe that's due to the fact that 1633 doesn't use as much solvent. And then we found that some expanded compounds outside the DIN method were also a little bit more difficult and needed some improvement in the chemistry. So let's take a look at the detection limits. And so for 537.1, the method detection limits vary by analyte, and they range from 0.53 to 2.8 nanograms per liter. Interestingly enough, 533 does not have method detection limits provided, so it only has lowest concentration minimum reporting limits, which is LCMRL. So 1633 is, it varies the detection limits by analyte and matrix, but for aqueous samples, its detection limit varies from 0.32 to 9.59 nanograms per liter. And for the DIN 17892, it isn't provided. However, it does reference an LOQ of about 1 nanogram per liter. So taking all this information and kind of considering, how can we make sure this system will meet requirements not only for these methods, but also beyond. You always have to, to determine your system's or your application's method detection limit, you need to determine that spike level for the MDL study, and then also make sure that you have the lowest calibration level in an acceptable point so that your system can actually detect as well that concentration. So go back to the chart we looked at before when we were looking at the blank background on the system. And again, when you look at all the EPA methods, you really have to kind of put it at a lower level to make sure that you can go beyond what the methods are saying. So again, we're going to zoom in right here at that 1 nanogram per liter level because we think that should be the MDL or MRL spike level. And so when you're spiking at that level, you also need to make sure you're calibrated below that level. So here's our spike level of 1 nanogram per liter in this blue dotted line. And you can see the dips are due to the fact that we've corrected for the salt form of the compound. And then our spike level is actually 0.1 nanograms per liter sample concentration. So you can see, or excuse me, our lowest calibration level is 0.1 nanograms per liter. So we're able to detect it on our analytical system. And that way we can make sure that we are going to have the lowest method detection limit possible. So from there, you can see this is our calculated MDL on the Prep Expert 8 system. It is in this blue square line. And we also have, for reference, I have added the 1633A MDL. This is what's in the method. So you can see our spiking consistently lower and calibrating consistently lower than the EPA 1633A method allows you to accomplish a method detection limit that is lower than the industry standard, which was nice. It allowed us to make sure that our system not only can meet all the MDL requirements of EPA methods, but also, beyond that. So now that we have gone over the PFAS system acceptance criteria, that was the low PFAS background, precision and recovery, and the method detection limit, let's dive into some PFAS operational improvements and see what we can do in our labs to make sure that we are operating at the most efficient rate we can, and also making sure that our methods are robust. So when I think of operational improvements, I think most labs will agree that sample throughput, especially for, a lab that's processing hundreds of samples, maybe even thousands of samples a week, sample throughput is by far the most important. Making sure that you can process all your samples and have good turnaround times for your clients is highly important. And so when we look at just the sample prep time that it takes to do the SPE portion of the extraction, we can see that most of the EPA methods and the DIN methods, total prep time on the Prep Expert 8 is below 2 hours. However, EPA 1633A is greater than 2 hours. It's 2 hours and 35 minutes to process your samples. So it's an 8-channel system. It processes 8 samples per run. So you're basically taking 2 hours and 35 minutes to process 8 samples, which for some labs might be fast enough and meet their requirements. However, many labs are looking to improve that. And so since this is a performance-based method, we can make some adjustments and improvements to make it more streamlined. And when you look at this, you see the biggest bottleneck in this method is it processes 500 mils of sample at 5 mils per minute. That's what it recommends. So we took a look at this to see, can we improve this? Can we increase the load rate to make this a more efficient extraction? So optimizing sample load rate is very important if you want to improve your efficiency. And you can see from here, I have created a chart. The blue line is for 500 mil sample volumes, the orange is 250 mil sample volumes, and the gray is 200 mil sample volumes. And on the x-axis, we have the sample load rate in mils per minute. And then on the y-axis, we have the total time. So this is just loading your sample through the SPE cartridge by itself. That's the time it takes. So when you're loading at 5 mils per minute, you can see obviously the 500 mil sample takes much more time. And so this is the challenge with 1633, since the method, most people are running 500 mil sample volumes in this method and loading at 5 mils, that's where all the time is spent, is basically sample load. But if you were to increase that load rate, you can see that you drastically start reducing the time it takes to process or load that sample. The nice thing about the Prep Expert 8 is you can run it in split mode, split method modes, meaning on one side, four samples, I can extract one method, and then on the other side, the four samples, I can extract another method. So this is actually really useful. I took a picture when we were doing this method development, and I did 1633A method, and I did it standard at 5 mils per minute. And then I did on the other side, the right side, I ran the same exact method. The only thing I changed was the sample load rate. And you see 30 mils per minute. And you can just see right there the time difference, 2 hours and 37 minutes versus an hour and 4 minutes at a 30 mil per minute load rate. So let's take a look at the data. So here's our sample load rate evaluation, and these are the 1633A natives recoveries. Again, we spiked at this concentration range of, this was a mid-range 22.2 to 625 nanograms per liter. And what you'll see is, for the most part, in our blue, or excuse me, the orange, the blue, and the gray, these kind of cluster together right here, all kind of follow the same performance in terms of recovery. Now, you can see that the 25 per mil per minute average, you could see we were starting to get some that were falling outside of the acceptance criteria. And the 30 mil per minute average, you could see we're getting a few that were way outside of the acceptance criteria. And then you can see overall, we were kind of getting a lower recovery, and that's due to the EIS being also recovered low. So there is the EIS was being recovered high. And so there was a variance that we set at 30 mils and at 25. That was a little bit too much. So actually what we found for our study at this concentration, 20 mils per minute was our sweet spot. You could probably also do it at 15 mils per minute, but we decided to move forward with 20 mils per minute since that was gave us good performance data and met our 1633A requirements. So now that we have made our sample load rate more efficient at 20 mils per minute, you can see our time now to extract 8 samples is now 1 hour and 35 minutes. So more aligned with what the other methods are doing. The next thing that we will talk about is improving our solid phase extraction chemistry. And what you'll notice in the EPA 1633 method is there's this cleanup that is done to the extract. It's a carbon cleanup where you add 10 milligrams of carbon to the extract that's eluted from the system, and then you shake. And it takes, another 15 or so minutes just to do this portion. And then you'll notice that in our our extended DIN method, we actually had to add a dry time of 20 minutes to our dry our SPE. And I'll get into why that was done. But let's talk about the chemistry for a bit, the SPE chemistry. So a lot of labs have elected to instead of adding the carbon to the extract, the loose carbon to the extract, there is some variability. You can lose recoveries of some compounds if you add too much carbon or you let it sit in the extract for too long. So a lot of labs have actually decided to stack, a carbon cartridge or on the top or the bottom, depending on what they're doing, and then a wax on cartridge as well. So kind of doing it all in one step when they load the sample. We actually have developed a blended uh, cartridge that has the wax media and the GCB blended into one column. And the blending versus the layering is important because blending allows you to actually blend less carbon in the actual cartridge so that you don't have as much susceptibility to losing analytes of interest because you're using 50 milligrams of carbon when the method really only tells you to use 10 milligrams of carbon. So blending allows you to use much less carbon, and so you kind of get the best of both worlds when you're blending it. And then also we've developed this, and that's usually used for the 1633A method. But for the DIN method, labs are using a layered DVB and wax cartridge. So it has the weak anion exchange sorbent in one layer, and then the divinyl benzene hydrophobic sorbent in another layer. And we've developed this as well. It's our Evolute PFAS Plus column, and we'll kind of go into a little bit why that's helpful in getting some recoveries up. So first things first, this is our Evolute Wax GCB blended cartridge, and it just shows you some recoveries for some of the 1633 natives. And what we have here is in the blue bar, we have the average recovery for a low level spike. So spiking at the, lowest level, the MRL level, and then an OPR or a mid-level spike in the orange. And what you can see is, overall, and I just added the arbitrary plus or minus 30%. I didn't actually include the 1633A because 70 to 130 is actually more strict than the 1633A recoveries. So I just use those for a marker for this. But you can see all the recoveries for both the low and the mid-level fall well within the 70 to 130. So definitely meet the acceptance criteria for 1633A. One thing that you will know, which is interesting and is also why we like the blended version, is the low levels. When you compare them to the mid levels, you can see some start to dip pretty close to the 70% recovery. So it is important that you don't, especially for low level spikes, that you make sure that you're not using too much carbon, and that's why we like the blended because it allows us to use less carbon than when you actually layer it in the cartridge. Now let's take a look at the Wax DVB or the Evolute PFAS Plus cartridge. And what we did here is, here's the Evolute PFAS Plus. It's the Wax DVB. We did 3 spikes at 10 part per trillion in reagent water. And then we looked at 2 different wax cartridges as well, which just have wax in them. And what you'll see is FOSA A is one of the compounds that really is difficult to recover, especially when you're just using wax. So having that extra DVB in the cartridge is very important when trying to recover this compound because it just doesn't recover as well with just wax or weak anion exchange sorbent. And then you can see here we have the octadecanoic acid. And so this is the 18 chain carbon that we talked about earlier. And you can see the recoveries for this on the wax DVB weren't as high as when we just used the wax. However, we were able to improve this. And if you remember earlier, in the slides that the DIN method, we actually added a 20-minute dry of our SPE sorbent. And that's because the wax DPB has more sorbent in it, so it actually retains more water in the sorbent. So you have to really dry that SPE media out. And that required us to increase that dry time to 20 minutes. And then we were able to get these recoveries improved. So we talked about, the throughput and how we can improve our throughput of our sample processing. We talked a little bit about SPE chemistry, the blended wax GCB and the layered wax divinyl benzene media. So now that we know kind of how to increase throughput and how to improve our recoveries, make our data a little bit more robust, let's talk about processing challenging matrices. And the Prep Expert 8, it is a tube-based system, so it does have its limitations, like any tube-based system, on processing really challenging wastewater samples. However, you can, as you can see in this video, you can use inline uh, syringe filters to actually um, remove any particulate from entering your SPE sorbent as you're processing your sample. And then here's some that are not using inline filters, and you can see, yes, the system will process those samples, but a lot of those um, particulates will actually get into your SPE, and you have potential for a clog. The system does have clog detection, so it'll let you know if a cartridge has been clogged. So that is helpful. But if you are processing really challenging wastewater samples, I highly recommend using inline filtration. It not only protects your SPE from getting clogged, but it also just protects your system and the longevity of your system. So highly recommend using inline filtration. So let's look at some data. These are groundwater samples that we processed on the system, and you can see how high the levels and the concentration of PFAS in these samples are. And the system was easily able to process them. We actually processed blanks after this. Of course, we did cleaning just to make sure the system can be cleaned after processing these high concentration samples. But you can see I zoomed in to my chart cuts off at 500 nanograms per liter, so you can see the detail of these samples. However, these right here, the ones that have their numbers on them, those actually expand beyond it. So you can see some of them have 8,000 uh, nanograms per liter plus uh, back of detection of PFAS analytes. But you can see, the range for different compounds and how they're found in these different groundwater samples, and the system was easily able to process that and be cleaned afterwards. So these are actually the extraction perform or the EIS recoveries. So these will give you kind of an idea. Not only these were associated with the groundwater samples in the last slide for the natives, but this gives you an idea of the extraction performance. Again, we decided for this to continue to run it at 20 mils per minute when we loaded our samples to keep that efficiency up. And for the most part, in all of these groundwater samples that had high levels of PFAS in them, all of our EIS fell well within the range. There were a few that fell outside right here, which was the 4.2 FTS. However, the laboratory that we were working with to process these samples, they actually would do multiple injections of these to make sure that they got, these ranges to be as accurate as possible, since they have to dilute these samples to actually get them to fit within their cal points. So this could have just been a product of instrument analytical inconsistency, but overall they were very happy with how well these samples processed and how well they fell within their acceptance criteria. All right, so we talked about the operational improvements sample throughput, SPE chemistry, and challenging matrices on the system. Now I kind of want to go into the features beyond PFAS testing. So one of the things that most labs are interested in is, okay, your system can run PFAS. What about other SVOC methods? And this is something when we designed the Prep Expert 8, we built into the system knowing that we wanted it to be able, one system to be able to switch from running PFAS methods to running SVOC methods. And what we did is we have these external lines that are interchangeable. So you can remove these lines and put in new lines. So we have two options. We have polyethylene and we have Teflon or PTFE. So the polyethylene are used for PFAS applications, and the Teflon or PTFE are used for SVOC applications. That is because, these methods typically use harsher solvents and they're looking for phthalates. And so making sure that you have solvent lines that are and sample lines that are compatible with the harsher solvents and won't give you any leachables is important. We did a study and we wanted to see how quickly we can change these lines. So it took about 2 hours to change the external lines and switch applications. And that includes purging the solvents from the system and the lines, detaching the lines, attaching new lines, and then cleaning the system with the appropriate solvents. And we went from SVOC applications to PFAS, and we did some blanks right after it, and there were we were well below the acceptance criteria for the method blanks on the PFAS, so it definitely worked. You can switch from SVOCs to PFAS testing within a day. So the beauty of this system that's different from other systems out in the market is its internal lines. The internal lines are PEEK. And so PEEK materials are compatible with both PFAS and SVOC methods. So all the lines that are inside the system, and here's a picture of the internal lines, the PEEK lines. All of those are compatible with PFAS and SVOC methods. So you don't need to swap out the internal lines, which is why one system can be used for both techniques. Now my first question or anyone's first question is, well, why don't you just use PEEK for the external lines? Well, the PEEK has poor bend radius, so these aren't very flexible lines. So if you bend them too sharply, they will crack or they will kink, which is not a good thing. And so when you design a system, the internal components need to be designed to accommodate these PEEK tubing. So it's very important. It's very difficult to retrofit internal lines in a system with PEEK lines because they don't have great bend radius. And so you need to make sure that when you're designing the system, you're accommodating the poor bend radius of these lines. And that's something we were able to do, which makes this system very powerful because it can switch from the PFAS applications to the SVOC methods. So the next thing on PFAS is column stacking. One of the things that you'll notice in our Prep Expert 8 is it has a very tall it has a lot of space in its SPE platform. So your SPE cartridges connect here, but there's a good amount of space to stack columns. And there's a few applications you can do. You can have two SPE sorbents stacked, kind of like we mentioned for 1633 with the GCB and the wax media. Or you can do inline drying with sodium sulfate for an SVOC method. The nice thing about our system is, when you're running your aqueous sample through, and this is for nitrosamine, we did a nitrosamine study on the system. Actually, when you're running your aqueous sample through the carbon, you can't obviously stack a sodium sulfate in there, or it'll immediately clog up from your aqueous sample because you process about 200 plus mils. But what you can do is have the system turn blue after it's done processing your sample. It'll pause and it'll wait for you to connect your sodium sulfate cartridge and then do inline drying of your extract when you go to elute your compounds of interest. So that's really, really nice, and it's a visual indicator that, hey, I'm ready to have my sodium sulfate cartridge added and move on to the next step. So last but not least, the collection options I think are really what sets the Prep Expert 8 apart and all allows it to be very useful for applications beyond PFAS. Being able to collect in different types of vials, especially when you're doing inline drying, is very useful. And again, as you saw with our SPE platform, the collection rack or the collection platform has a lot of space, and it has these adjustable bars that allow you to adjust the for the length of the tube. So this is actually really useful. We tested this. We fitted a bunch of different collection containers and a few that have, these 1 mil tips for endpoint. So a lot of SVOC methods, when you do the final concentration, you want to end at a 1 mil or a half a mil concentrate. And so we actually built the system so it's compatible with various different, and these are all the collection vials that we've tested. I'm sure there's more out there, but you can see the different types of collection vial options. So if you're using an SVOC method, you can not only do the column stacking and do the inline drying, but you then can also collect in a concentration tube, like a turbovap tube, so that your downstream concentration workflow is complemented in the same system. So from there, we covered a lot and want to make sure that we kind of go over the main points. And in summary, the system really demonstrated that it meets the acceptance criteria for not only the EPA methods, but the DIN requirements. And that includes the PFAS background levels, and those are below 0.1 nanogram per liter, which exceeds the EPA and the DIN requirements. Precision recoveries results exceeded the both requirements as well. And that was done at both low and high spike levels, so anywhere from 1 to 625 nanograms per liter. And then method detection limits, we met both EPA and DIN criteria, with a majority of the DIN method detection limit less than 1/3 the MRL, or 0.33 nanograms per liter. For the PFAS operational improvements, we found that, it is possible, although you'll probably want to test it in your lab and make sure, because it might vary with spike levels, but it is possible to improve your throughput by increasing the sample load rates. We found that maybe 15 and 20 mils are good spots to start in terms of sample load rate. And then for SPE chemistry, we found that, with the wax GCB blended, it helps allow you to kind of limit the amount of carbon that you blend in your sorbent when compared to a layered, so that you don't have the chance of losing some of your analytes, especially when you spike at low levels. And then the layered wax DVB format is useful, especially for FOSA A in terms of recoveries. However, when you're using more media, you have to make sure that you're drying your SPE column, because some of those more uh, uh, longer chain PFAS are going to be more difficult to elute if your SPE column isn't as dry. So you got to make sure that you're considering that as well. Also, we showed you that the system is capable of processing challenging matrices, although we highly recommend inline filtration. It will make sure that your SPE cartridge doesn't get clogged, and then it also will protect your system. And we've have comparable results with manual extractions. And then for features beyond PFAS testing, we showed you that the system can easily convert from PFAS to SVOC methods, and that is all done on the same system. So there's no need to buy a system that is plumbed for SVOCs because the system it just has the external lines that need to be swapped, and that can be done with less than 2 hours, and that includes cleaning and purging and getting ready for your next application. We also showed that system can do cartridge stacking, so you can stack 1, 3, 6, or 15 mil columns, and that'll allow you to do dual stage SBE. You could probably do the inline drying if you're doing SVOC methods, as well as other applications such as cleanups, fluorosil, silica. There's pretty interesting ways you can take the column stacking, in my opinion. And then finally, we went over some collection options. The system allows you to use a variety of vessels for collection, and a lot of them, like the 50 mil turbovap tubes that have the 1 mil endpoints, that allows you to really go straight to your downstream evaporation workflow and not have to do any vial transfer or anything like that. And with that, I'd like to thank you for joining us. I've referenced the EPA as well as the DIN methods to the right. And we also have a QR code if you're interested to learn more about the Prep Expert 8. There's the landing page for our website. And thank you for joining us. And I'll take questions.
Well, thank you, Evan, for that excellent presentation. We now have time for your questions. So, Evan, our first question is, how should a lab decide which automated platform best fits their needs?
Yes. So I guess the three, well, I guess the question is more for the three systems that I showed in the very beginning, the Extra Hera, the Prep Expert, and the Horizon 5000. And really the biggest thing is first is your application. Are you looking to do SVOCs or PFAS analysis? Second thing would be your sample volume. So is it below 50 mils? Or is it above 50 mils? The extra Hera when you're doing low volume processing, such as, for solid extracts and soils and whatnot, it's really high throughput. It'll process, 24, 48 or 96 samples in, less than 2 hours. So obviously, you have to have the right matrix and volume for that system, but if that's what you're looking for, that's the way to go. Now, as for the Prep Expert and the Horizon, those are for the larger sample volumes. Above 50 mils is where they really shine. And again, when you're deciding between those two systems, it's whether or not your samples are extremely challenging. So the very, very challenging wastewater samples, you might want to consider looking at the Horizon 5000, but the Prep Expert 8 is great for everything in between.
Thanks, Evan. That's great. We'll take our next question, which is, does the blended wax GCB sorbent format meet the compliance requirements of EPA method 1633A?
Yes, that's a great question. So 1633A is a performance-based method. So as long as you are able to demonstrate that your QC requirements are meeting the acceptable method requirements, then you can switch from blended to stacked to layered wax GCB. So yes, it is acceptable as long as you demonstrate it in your demonstration of capability.
Okay, great. Thanks, Evan. I think we've got time for one more question. Beyond PFAS testing, what additional applications can the Prep Expert 8 be utilized for?
Yeah, that's a great question. So, as we're launching the system, our primary focus for the system launch was PFAS testing. However, we've expanded and we are continuing to expand into SVOCs, and we've looked into nitrosamines. We're going to be looking into pesticides and PCBs. So really, the sky's the limit in terms of the applications because the system is suitable for both PFAS and SVOC applications. And so, yeah, feel free to reach out to us if you're interested in kind of going beyond PFAS testing with the Prep Expert 8.
That's great. Thank you, Evan. I think we'll leave it there. If any other questions do come in, I'm sure that Evan will be happy to respond to them via email. Thank you also to our scientific partners in this webinar, Biotage. And with that, I'd like to thank you all for logging in and watching. Thank you and goodbye.